We've learned the sum and difference identities for cosine. There are different sum and difference formulas for sine and for tangent. So we're going to jump into learning those. For the sum of a sine, and it looks very similar to the cosine one, so make sure we understand the differences. For the sum of sines, it's sine of the first value, cosine of the second value, plus or minus the cosine of the first value and the sine of the second value. Couple things to notice here that are different. Number one, do I have the flipped over symbol in between? No, that means plus, minus means minus. But I do mix and match the sine and cosine on both sides. So in the cosine version of this was cosine times cosine. In the sine version of it, it's sine times cosine both times, switching the angle. For tangent has a more complicated but still really easy to use formula. The formula is tangent of A plus B, or minus A plus A minus B, is the tangent of the first angle plus or minus the tangent of the second angle, all divided by 1 minus plus the tangent of A times the tangent of B. So some things to notice here. In the numerator, regular plus minus. In the denominator, flipped. So if you are doing the sum of tangents, that's a plus on top, minus on bottom. If you're doing the difference of tangents, it's a minus on top, plus on bottom. Okay? So if you're doing the sum of tangents, so if the plus sign is what you see in your little one, you're going to have a plus on top and a minus on bottom. If you see a minus in the little one, you're going to have a minus on top and a plus on bottom. Okay? Now we can use this the same way we use the cosine formula. So let's find some exact values. If you have to flip back to that little table I gave you for the one that's in radians, we can. But we'll find the exact value of sine of 75 degrees. Using some typical angles, what's a way we can make 75 degrees? 45 plus 30. So we're actually going to evaluate the sine of 45 degrees plus 30 degrees because we don't know anything from our unit circle about 75 degrees. But we do know this one. So if we expand it using the sum of sines, not cosines, that means that we're doing the sine of 45 degrees, the cosine of 30 degrees, plus the cosine of 45 degrees times the sine of 30 degrees. Okay, let me highlight this so it makes sense. So we have our first angle, and so here's the first angle in the formula. Here's our second angle. Here's a second angle in the formula. Now, all of these values are things on a unit circle we know. What is the sine of 45 degrees? And what's the cosine of 30? The cosine of 45 is also square root 2 over 2, and the sine of 30 is 1 over 2. Top times top, bottom times bottom. We can simplify this to square root 6 over 4 plus square root 2 over 4. And then one giant fraction as square root 6 plus square root 2 over 4. And again, the square root 6 and square root 2 can't combine by addition, so we have to leave it exactly like that. That's an exact value. For number B, our first tangent, okay, you might have to flip back to that table I gave you, but is there a way you can add or subtract some values we know, some angles we know to get 7 pi over 12?
Do you want the reduced version or?
Whichever way makes sense to you.
Pi over 4 and pi over 3.
Pi over 4 plus pi over 3. Yes, because that is 3 pi over 12 plus 4 pi over 12, which does make 7 pi over 12. Now, when we use tangent, we're going to be careful because we're dealing with fractions. When we expand this is the tangent of pi over 4 plus the tangent of pi over 3, all divided by 1 minus the tangent of pi over 4 times the tangent of pi over 3. So a couple things to notice. Here's our first angle, first angle, second angle, second angle, second angle. We turn to our unit circle to find these actual values. What is the tangent of pi over 4? Ooh, that's nice. What is the tangent of I almost said the answer. Pi over 3. And then if I go to the bottom, this is 1 minus. Again, tangent of pi over 4 is what? 1. And tangent of pi over 3 is square root 3. What's 1 times square root 3? Square root 3. Now, some textbooks would let you stop here, but it's not mathematically correct if there is a radical in the denominator. So to get the radical out of the denominator, we have to rationalize, meaning we are going to multiply both the top and bottom by 1 minus square root 3. I'm sorry, by the opposite, by plus. You multiply the opposite, yeah. It's called the conjugate, not the opposite. I can use correct words. So when we do this, it does get a little bit complicated, but the numbers should turn out to be really, really simple. On the top, you're going to expand using FOIL. 1 times 1 is 1. 1 times square root 3 is square root 3. Square root 3 times 1 is square root 3. And square root 3 times square root 3 is 3. The bottom is technically the difference of two squares. So if you remember the pattern, it's the first thing squared minus the second thing squared. Now a whole bunch is going to cancel out or reduce here. In my numerator, I see I have 1 plus 3. That's easy. 1 plus 3 is 4. And then I have 2 square roots of 3. So I'm going to write that as 2 square root of 3. In my denominator, 1 squared is 1. Square root 3 squared is what? 3. This becomes 4 plus 2 square root 3, all divided by what? Negative 2, which you can also reduce down. Since 4 and 2 are both divisible by negative 2, you can reduce this to negative 2 minus square root 3, which is me just doing 4 divided by negative 2 is negative 2, and 2 divided by negative 2 is negative 1. You can't divide into the radical, just any number in front of it. If these numbers weren't both divisible by negative 2, I would have stopped here. But since they are divisible by negative 2, you can go one step further in reducing. Now we can't forget about C over here. In number C, we now need to start recognizing which of the sum and difference formulas we're using. What I've always noticed is that if sine and cosine are mixed and matched, it's sine. So this is the something of sines. So when I combine these down together, it would be the sine of 40 degrees something 160 degrees. Am I adding or am I subtracting? Subtracting. Because with sine, it's the same thing. No change in the symbol, but you do mix and match the sine and cosine. Well, 40 minus 160 is negative 120 degrees, which you might be able to know right off the top of your head looking around your unit circle, but we don't have the negative angles listed for our unit circle. So why don't we use its coterminal angle, meaning we add 360 degrees to this. Negative 120 degrees is the same as positive 240 degrees. Again, I got that by adding 360 for its coterminal angle. Now look at your unit circle. What is the sine of 240 degrees?
Negative 4 pi.
That's the radian version of it. I want the x value of the coordinate.
Negative radical
Mm-hmm. The x coordinate is, or sorry, I said x coordinate. I mean y coordinate because it's the sine coordinate. That was on me. My bad.
When it's cosine, it's the x.
Correct. Coordinates on that unit circle are cosine comma sine. Let's go ahead and expand these and write them again as terms of theta alone. So we're hoping that when we expand them using our identities, we'll be able to get rid of any degree or radian and just have an x or a theta. I'll do the first one and then I'll let you guys practice the other ones. So for this one, if we go ahead and change this to the sum of sines, we'd have the sine of 30 degrees times the cosine of theta plus the cosine of 30 degrees times the sine of theta. We know the values for 30 around our unit circle. The sine of 30 is a half, and the cosine of 30 is square root 3 over 2. I notice now that both the first term and the second term are divided by 2, which means they have a common denominator of dividing by 2. 1 times cosine is cosine of theta, and square root 3 times sine is square root 3 sine theta. Once I get it written in terms of only theta and written in a reduced version, I'm done with this. I'm going to let you guys try B and C. B should remain as a fraction, but a really simplified fraction with no numbers showing other than a 1. And then the last one should reduce all the way down to 1 trig function. So you guys go ahead and try B and C for this page. I'm going to go ahead and start working these just to see where we're at. Yes. Since the tangent of 45 degrees is 1, we can get here, and then we just need to simply reduce or just clean up that denominator. 1 minus tangent of theta and then 1 plus tangent of theta is actually where you'd stop. You would not have to do any sort of multiplying like we did on the last problem. We only did that on that problem on the front because we had to rationalize the denominators. Tangents are allowed to be there. Square roots are not. For this last one, sine of 180 minus theta, it's the difference of signs, so I would use the sine formula, but with a subtraction sign. Sine of 180, cosine of theta, minus cosine of 180 degrees sine of theta. Sine of 180 degrees is 0. And the cosine of 180 degrees is negative 1. So that whole first term cancels out because it's multiplied by 0. I end up with negative times negative, which is positive. This should end up just as sine of theta. Because we're subtracting a negative. Minus minus is positive.
Oh, we keep them.
Yeah. Okay, when we flip to that last page, example 3 is going to be the one where we create a sidebar. So if you notice, in this problem it says, suppose that A and B are angles in standard positions such that sine of A is 4 over 5, and A is between pi over 2 and pi. Cosine B is equal to negative 5 over 13, where B is between pi and 3 pi over 2. Let's figure out what that's even telling us here before we even look further on the problem. In this problem, this part right here where it says A is between pi over 2 and pi. Look on your unit circle for pi over 2 and then for pi. What quadrant is that is contained by pi over 2 and pi? It's the second quadrant. So we're saying that this sign, or that A ends in the second quadrant. Now what about B? Between pi and 3 pi over 2 is which quadrant? Quadrant 3. So we know when we set up our little sidebar that we're working in quadrant 2 and in quadrant 3. So here's my little sidebar. Since I know I'm going to need these values, we'll go ahead and do this over here. We'll have one side be A and one side is B. So just like we did on the problem before, let's take these values and figure out what we're missing. And we'll take these values and figure out what we're missing. Okay. Since for the A angle, they told us that it is sine, did they tell us X, Y, or R? Which ones? Y and R. And again, a Pythagorean triple means that X is what number? 3. It's in quadrant 2, which means it's negative. For B, cosine of B is negative 5 over 13. So what numbers should I put where? X and R, so negative 5 and then 13. Again, it's Pythagorean triple. Do we remember the other one? 12. But this is in quadrant 3. So it's negative. Quadrant 3 is the negative quadrant. So both X and Y are negative. All right. Yes. On your unit circle, you have these quadrantial angles of 0, pi over 2, pi, and 3 pi over 2. So the first part says that A is between pi over 2 and pi. That means it's in this quadrant. And then the second one says it's between B and 3 pi over, between pi and 3 pi over 2, so it's the third quadrant. Yeah. All right, let's look at the actual question here. It said, find each of the following. We're going to do the sine of alpha plus beta. Wow, I just switched to Greek letters. Sine of A plus B, which means this is going to be the sine of A times the cosine of B plus the cosine of A, the sine of B. We just need to get those values from our sidebar. Yes?
So it doesn't matter that, like, cosine is negative in quadrant 3? Like, you wouldn't make cosine negative?
I will, yes. It is, so it told us it's a negative number. That means that the negative goes to the x value, not the radius, which is why I made the x value negative. And the y value will also be negative because in this quadrant, to have any sort of coordinate points in that bottom quadrant, x and y both have to be negative. Just like regular coordinate grid geometry. X and y both have to be negative. So if we fill this in, again, we don't actually know the values of A and B, but we know the values of the triangles they create. So the sine of A is going to be the y over r from the A sidebar, which is 4 over 5. Now, of course, they gave us that one in the problem. And they also gave us cosine of B in the problem. But I can get those values from my sidebar because I know the x, y, and r for each of those angles. What should I write down for cosine of A? Negative 3 over 5, because cosine is x over r, and I know the x is negative 3, and the r is 5. What about the sine of B? Negative 12 over 13. Now, of course, like the problem before, if you're using a calculator, you could go straight from here to the answer, but if we're going to practice doing some mental math, top times top, bottom times bottom. 4 times negative 5 is negative 20. 5 times 12 is 60. And then negative 3 times negative 12 is positive 36. And 5 times 13 is 65. I wrote down the wrong number, didn't I? This should be a whole 13. Sorry. Since they have the common denominator, we can write them as one fraction and actually do this math, which makes this 16 out of 65. And that is as reduced as it can get. Now, using the same sidebar, we've already found x, y, and r for both angle A and angle B. Can we do the tangent? And by we, I mean I'm still going to do it with you. Okay, let's fill out the tangent formula, but I'll go slowly. For tangent, it would be tangent of A, and then what symbol? Plus the tangent of B divided by 1 minus tangent of A times tangent of B. If we fill this in, tangent of A, okay, tangent is y divided by x. So for the tangent of A, what should I put in that top of the fraction right there? 4 over negative 3. Move my plus sign a little higher. What about the tangent of B? Negative 12 over negative 5. Yes, I know it becomes positive, but for right now, for our notes, we know where we got those numbers from. Let's put both negatives. In the bottom, we would have 1 minus, and then those same values, because again, I just already found them. So it's 4 over negative 3 and negative 12 over negative 5. Again, put the negatives there so later on when you're looking back, you know where they came from. At this point, we just need to do a whole lot of arithmetic with fractions. In the numerator, we cannot add those until they have a common denominator. What's going to be the least common denominator between 3 and 5? 15. So I'm gonna stick the negative up in the top here. This is going to end up being 15 and then 15. I had to multiply 3 times 5 to make 15, so 4 times 5 is 20, but we make it negative, so that the negative sign is still there. 5 times 3 is 15, so 12 times 3 is 36. I'm going to let the negatives go on that one. Negative times negative is, or divide by negative is still positive. Okay, but for the denominator, I don't have to have a common denominator to multiply fractions. It's just top times top, bottom times bottom, which means this ends up being 1 minus negative 48 over positive 15. Negative 20 plus 36 is 16 fifteenths. And in the bottom, you have a negative negative, so it's like we're adding those. So 1 plus 48 over 15 is 15 over 15 plus 48 over 15, giving them a common denominator. It's 63 fifteenths. Again, I made this 15 over 15 to actually add those. Ooh, now we're dividing fractions. Y'all know these rules now. What's the rule on dividing fractions? Oh, yay. Keep, change, flip. I notice now that you have a 15 on both sides. They cancel out. This is 16 over 63. Ooh-wee. But of course, when you're doing these kinds of problems with a calculator, you could go straight from here to here if you type it in correctly.
Make sure you use parentheses.
Use lots of parentheses, absolutely. Now this question here, we now want to figure out what quadrant A plus B ends up being in. So let's think about this for a second. When we did the sine of A plus B, we got a positive number, bless you. When we did the tangent of A plus B, we've got a positive number. So if we go back to this guy, based on the sine being positive and the tangent being positive, what quadrant am I in? Quadrant 1. So again, that's using problems A and B. In problem A, the sine of it was a positive number, and in problem B, the tangent was a positive number, so the only quadrant where that happens is quadrant 1. Last problem here before spring break. You're done listening to me. All right, we're going to verify this identity. We have sine of pi over 6 plus theta plus cosine of pi over 3 plus theta equal to cosine of theta. Obviously, this is the more complicated side. So let's work with that side. Do we have a formula to expand the sum of sines? We do. That would make this the sine of pi over 6 times the cosine of theta plus the cosine of pi over 6 times the sine of theta. Yes, we see that? Do we have something that we can use to expand cosine?
Yes.
Yeah. Think back to the section right before this. What is the formula for cosine, though?
Cosine of pi over 3
Mm-hmm.
times cosine of theta.
Mm-hmm.
Or minus
Mm-hmm.
sine of pi over 3 times sine of theta.
Oof. We have expanded both. So if I'm writing a step here, I know that that's going to be equal. So that was the sum and difference identities. All right, let's use that unit circle. We're using a unit circle because I see I have sine and cosine values for actual angles here. Let's find out what they are. What is the sine of pi over 6?
Okay.
1 over 2. What is the cosine of pi over 6?
Square root of 3 over 2.
Mm-hmm. How about the cosine of pi over 3? 1/2. And the sine of pi over 3? So the step we did here, we just used the unit circle. Okay, lots of things are going to happen at once. Something really cool that makes this very small, very quick happens. Do you notice that you have a positive square root 3 over 2 sine and a negative square root 3 over 2 sine? They cancel. Oh, goodness. Hallelujah. Okay, goodbye, goodbye. What else do you notice is happening here? There's two 1 over 2 cosines. So if you have two 1 over 2 cosines, that's just a single cosine. Isn't that what we wanted? That was our goal, was to get this to be equal to cosine. So if I write down my last few steps here, since I went really quick, this was a cancel step and technically combined like terms, and then we just multiplied. And we have verified that identity. So now, adding on to what we learned in section 5.1 and 5.2, which were the typical identities for trig, you now have the sum and difference identities for sine, cosine, and tangent that you can use in these different kinds of problems.